I'm sharing my screen. So good afternoon. We're Team 24, and today we'll be presenting our topic, the Smart B2B AI Ordering System. Our project focuses on improving how B2B companies browse and search and order gate and crown panels through an AI-powered platform. In many companies, product ordering is still handled manually, either through calls or spreadsheets or even messaging platforms. This creates a lot of confusion and is quite an efficient process. It makes it very difficult to store extremely large catalogs efficiently. To solve this, we built a full stack web platform that integrates multiple AI techniques, which include Semantic Vector Search, an LLM recommendation assistant, and a Retrieval-Augmented Generation system, or RAG. The goal of our system is to help users find products more naturally. They would receive intelligent recommendations, and they would be able to interact with the catalog data in a more efficient and user-friendly way. One thing our team is proud of is that we successfully implemented all the major components of our original proposed architecture into our final working system, including the front end, back end, AI service layer, vector database integration, and even the end-to-end AI workflows. So at this point, I'll hand it over to my teammate Pin. He will walk us through the problem statement, the motivation, the system architecture, design decisions, and some of the implementation details. Over to you, Pin.
Thank you, Shannon. Okay, and first, let's look at the problem and the motivation behind this project. We identified several key issues with traditional B2B workflows, like large product catalogs are difficult to search. Standard keyword search often misses the user's actual intent. Manual ordering is slow and error-prone, which turns sales representatives into bottlenecks. Finally, there is a lack of intelligent product recommendations. Our motivation is to streamline these B2B ordering workflows and enable semantic product discovery. We want to use AI to improve decision making and provide grounded AI assistance. To achieve this, we built an AI-powered B2B platform that combines semantic retrievals, structured LLM outputs, and RAG to modernize industrial ordering workflows. Okay, next slide, please. Okay, next. Let's discuss our target users and use cases. Our system is designed for B2B buyers, organization admins, and suppliers. And here is our main workflow. The users begin with logging in. They can then browse the catalog to explore products, and this leads to our semantic search feature, allowing users to find items by meaning. For example, a user might query for a lightweight gas panel or something else. The system then provides personalized AI recommendations. Finally, the user can place an order, check out, and track their order to monitor delivery. Okay, next slide, please. And to support these features, we designed a high-level system architecture. We separated our concerns into distinct layers. The first is front-end. The user accesses the front-end client via a web browser, which is built with Vue 3 and Tailwind CSS. Second is about the backend. Our backend service is built with Go and the Gene framework, handling modules like authentications and catalog management. This connects to a PostgreSQL 16 database utilizing the pgvector extension for data storage. And third is our AI service. We have a dedicated AI service built with Python and Fast API. Our Go backend uses an AI proxy module to route requests here. The AI service handles our three main techniques, the vector search, the LLM Assistant, and the RAG pipeline. And finally, our external API. Our AI pipeline security communicates with the external cloud API for our LLM capabilities. Okay, next slide, please. And here is a closer look at our technology stack and the design decisions behind them. For the front end, we choose Vue3 and Tailwind because they allow us to build a fast and a single page application UI. For the backend, we selected Go and Gene for their high performance and the ability to create clean APIs. For the AI services, we use Fast API and Python due to their excellent compatibility with the AI ecosystem. And lastly, for the database, we utilize PostgreSQL along with pgvector to enable vector similarity search capabilities. Okay, next slide, please. And let's dive into the backend architecture and the design patterns. We implemented a layered architecture. This includes the handle layer, the service layer, the repository layer, and the database layer. For the handler layer, it's the HTTP or gRPC entry points. And second, the service layer containing our business logic and rules. And the repository layer for data access abstraction. The database layer is for persistent storage. For security, we use JWT authentication. The client sends creditor, credit, credentials. The server signs a JWT token. The token is sent with every subsequent request, and our middleware validates and decodes it. We also implemented a role-based access control. Clients can browse, purchase, and view only their own orders in the browser, and admins can manage products and view all orders in our system, and super admins have full system access and handle user management. And let's cover the project's background and architecture. I will now pass it over to my team members, Shannon. Thank you.
Thank you, Pin. I'll continue by explaining the AI techniques that we integrated into our platform. So the first AI technique is semantic search. So as we know, traditional keyword search only matches exact words like maybe Google search in the past. So if a user searches for something like maybe what materials are available for crown panels or a lightweight outdoor gate, a normal keyword search would probably fail to match the product description correctly if it used any kind of different wording that did not match with the database. So to solve this, we implemented a semantic vector search using embeddings. So in simpler terms, embeddings would convert that text into numerical vectors, and those numerical vectors would help capture meaning instead of the exact wording. So when a user enters any search query, the system converts that query into embeddings, and the embedding model would then compare it against the other product embeddings that we have in our PostgreSQL using pgvector. It would do a pgvector cosine similarity search. So this allows the system to return products that are semantically related to the user's intent, even if the keywords don't match exactly. During testing, we observed that the semantic search consistently returned more relevant results compared to traditional keyword-based matching, especially for natural language queries. Our second AI technique is an LLM Assistant. So this feature helps us receive intelligent product recommendation and configuration guidance. For example, a user can describe what they want in natural language, such as, I need a decorative outdoor gate that is lightweight or corrosion resistant, or I need a lightweight decorative outdoor panel. So this request is then sent to Claude Haiku through our AI service, where the model generates a structured JSON response containing recommended product categories, features, and suggested next steps, similar to what we've done on our assignments as well. One important engineering decision we made was using structured JSON prompting instead of plain conversational text. This helped not only get better outputs from the AI, but also it made it easier for the front end and the back end systems to reliably process this kind of data. Again, during testing, almost all responses were successfully parsed into expected JSON formats, which showed that structural prompting is significant, structural prompting significantly improved the consistency and the reliability of the system. Moving on to our third and last AI technique that we implemented in our system is Retrieval-Augmented Generation, RAG. So the third AI feature we implemented is one of the common issues we notice with many large language models is hallucination. So the model would just generate information that sounds correct, but is not exactly any true information, or it's not grounded with the actual system data. So to solve this, our RAG pipeline first retrieves the most relevant products. So we've done like the five most relevant products for our tool here. So it would retrieve the most relevant products from the catalog using Semantic Vector Search, and those retrieved products are then injected into the prompt. These are sent as context to the AI before sending any requests to Claude. So this means that the model generates answers based on catalog information rather than just relying on its own general training data. So for example, a user could ask what materials are available for crown panels. So this is a screenshot from our tool. So it would get the top most relevant products, and then it would give the user an output like based on our catalog crowd panels. Crowd panels are available in the following materials: aluminum, wrought iron, and cast iron. So the system retrieves all of the information based upon the prompt, and it displays it to the user. During testing, we observed that RAG responses stayed much more relevant and aligned with our actual catalog data. So that's the major chunk of our tool, all of the AI techniques. So I'll move on to the code demo. We have deployed our code just through Docker rather than a link. So I will start my code walkthrough starting from that point. So I'll be starting with the Docker Compose file. The Docker Compose file has four services running together. It has the Postgres, that's the database. It has the Go backend service. It has our AI service, which is in Python, and it has our Vue frontend. So all of them run together, and one command runs everything. That is Docker Compose up build. So while we're doing the demo, I'm just gonna run the command. So by the time we're done with the code walkthrough, we'll have our product running. And then moving to the most important major chunk is our AI services. So the AI service, it implements all the three AI techniques. It starts at this file, which is the main py. We have all of our AI techniques here. We have our vector search, which uses a user query. The user query gets embedded and compared against products in the Postgres, and it uses cosine similarity search in order to help find what the user needs. Moving on to the second AI technique, we have the LLM Assistant. The user describes what they need, and then Claude returns a very structured JSON output, and it would be in this exact structure. And then the third AI technique is RAG. So it gets the top five relevant products from the database, and then this is injected into Claude as context when we're sending out the prompt. So maybe the next place that we can go is I'm thinking we can go to the backend service and start with the authentication. So authentication is where users are authorized to enter the tool. So we start with the handler file. So the handler file has all the HTTP endpoints for login as well as register. So this is the first file that receives any incoming request when we start our tool. And the service file here, it validates the password and it checks if the account is active and it generates a JWT token. It's basically the brain of the entire authentication process. And we also have like test files. These are tests that run whenever we do any push or any changes to our code. So we have 15 tests here. We don't need any database connection for this, as you can see. All of the things are mocked, so this can run independently on its own. So this is our backend service. I wouldn't go through everything, but maybe we could go through the catalog. So the catalog handler. So this is where the search endpoint lives. So we do our semantic searches here. This file would forward the AI search request to the Python service that I just showed earlier, the main.py. And maybe we can take a look at the model. So it would just basically show us the structure of our data. It would have a product ID, a name, category, description, price range, material, which would be what we would show the user or on the basis of what we would be searching. And then we do have an AI proxy. So Go does not directly do the AI. The Python does the AI, and this helps communicate or forward the request from Go to Python. And under our front-end client, we have all our front-end logic. We have our catalog view. I think this would be more meaningful when we look at the demo, but we have the catalog view, which would show us the entire catalog of all the products that are on sale. And the welcome view is just a place we've consolidated everything that we have developed during our project development phase. And finally, we have our CI pipeline. So our CI pipeline, it runs all of the tests, 30 tests automatically every time we push something to main. It runs two parallel jobs. So it runs the Go tests. We have tests for our Go file as well as the Python tests. For either of them, we do not require any database connection. Everything is mocked. Uh, so For example, you can see here, every time we do a push, the CI/CD pipeline runs these tests automatically. If all the tests pass successfully, then we get a green tick mark. And if we did mess anything up and some of the tests do fail, we get a warning, and then we could go ahead and correct our issues. So I was in the process of running our Docker system when we were giving the demo. And once we run the Docker system, our front end, the Docker system runs everything together in a consolidated manner, and you would be able to access the tool at localhost 3000. So this is our welcome UI or the welcome view that I talked about that has everything that we've implemented throughout the development phase. We have our AI techniques, our automatic management system, our test suite with 30 tests, our Docker deployment and CI pipeline. But just I would like to sign out and register to show you like starting from the registration process, how things would work. So I'm going to register as a new user. So I'm gonna do Shannon and Shannon, Shannon at mail.com and a password. So this is how we would create an account. Oh my God. Anyhow, see. So now I'll be logging in with my username and my password. Okay, it's fine. Uh, so when you open your vector database for the first time, since I've been like running this project for a while, you wouldn't see that option here, but when you would run the project for the first time, you would see a button here that says embed the database. So once you click on that button, the vector embeddings would happen and the entire database would be embedded for our AI techniques for the semantic vector search, for the LLM and the RAG system. So we have our three AI techniques, we have our order management system, and we have our tests and CI, like I showed you. So I'll be going to my catalog by clicking on catalog. This is my catalog view. This is the entire catalog, and we have different categories. We have frames, crown panels, MDF, glass, fittings, cutting. So this is my order assistant, which uses the AI techniques, and this is my search, which uses vector embeddings. So I could just say something like, and I go here. I am looking for some glass fittings, and it would search. And it would tell me where I can search. So it would tell me I need to go to category fittings. This is my estimated price range and the key features and the next steps. So I could go to fittings and I could just order something. I could send an order. And once I send an order, it would be in my orders here when I go to my orders. And your AI techniques work here as well. So if I want to look for a heavy gate for a warehouse entrance, it would tell me what are my options. And then I could go to my catalog and I could search like heavy duty industrial gate. So it tells me to go to frame and order a heavy duty industrial gate. And then maybe I would also need a hinge set if I need a gate. So I'm gonna check under fittings and hinge set. So I would go to fittings and standard hinge set. I could send the order out and then I would have my orders here. This is for the semantic vector search. For LLM, I need a secure automated gate for a factory with 5 meter opening. So it takes some time. It asks Claude, and then it tells me where I can find it. So uh, it tells me to go to frame, and it gives similarly to what we did earlier. I could go to frame, and I could find whatever I needed here to have a secure automated gate. I could go over these. What materials are available for crown panels? So it tells me what different materials are available. It could be cast iron, aluminum, or maybe I could just say something like I need a weather resistant gate. So first it would look for the top five. That's what RAG does, looks for the top five, and then it would send that as context to the LLM, and then it would look at our database and see, okay, based on your weather resistant gate, these are the best options. We have sliding frame gate, galvanized steel, which is naturally weather resistant. So details like this, that it being naturally weather resistant, do not actually exist in our database, but we know that we have material galvanized steel, and the LLM helps the user find a weather resistant material. So that pretty much covers the three AI techniques. They could search for whatever they want here, or they could go into the catalog and use the order assistant, or just do a vector search here. Uh, okay, I think we spent some time there. So I would like to go over just the performance and evaluation results, like how we evaluated how well our system does. Uh, so for evaluation metrics, we tested mostly. We didn't run any kind of code or something. We just tested how well it does. So for semantic search, we compared how, like initially we tried with traditional keyword search, and we found that semantic retrieval process, it does a lot better than a regular keyword search. And for LLM Assistant, we evaluated whether the generated output followed the required JSON format. That is how we evaluated, rather than just because there is a chance of hallucination without RAG. So we did notice that it did always give us the right JSON structure. And at least not always, but most of the time it did. And for RAG pipeline, we tested whether the responses remained grounded. And with RAG, we got the most success, I think. When we tested whether the response related with our catalog database, more often than not, it always did, because it first looks at the catalog data and uses that as context to search. So we had the best success rate with our RAG responses as compared to the semantic search or with JSON using our LLM assistant. Some of the lessons that we learned are semantic searches, it improves our search drastically because it does not just use the exact keywords, and structured prompting really matters, which is what we understood with the JSON responses, that the more structure it has, the better outputs we get, the more context we give it, the better output we get. And RAG drastically improves the trustworthiness of the system. Like we got the best outputs with the RAG system. Like when we asked it for weather resistant material, it just didn't hallucinate. It took the data first, and only out of the catalog data we had, it gave the user a response. And microservice separation simplified AI integration. If you did notice in our code base, we have everything separate. We have our separate services for everything, and it highly simplified our AI integration, only integrating AI where it was necessary and in the right way. So right now our product data set is relatively small. So maybe future improvements could be using larger data sets and see how well the AI works, and maybe fine tune the recommendation models, give real-time analytics. Maybe right now we support only English, but we could support different languages and maybe have a hybrid retrieval pipeline. So that's it from my end. So we'll be signing off for the semester. And also with the video, we will be submitting it over email since Canvas is down. So thank you for a successful and nice semester. I'll stop the recording.